recording. So we're very pleased to have Jeremy Rouse here at our seminar today from Wake Forest, and he will be speaking to us about integers represented by positive definite quaternary quadratic forms in the Petersen inner product.
Thank you very much for the invitation to come and speak in this seminar. It's great to do this. I confess I'd been invited in the past and I wasn't able to make it because it's actually pretty far from Wake Forest to Vanderbilt. So it's a pleasure to be here, and I want to thank all of you for coming. I know that everyone is probably having a tough time with all the restrictions that are happening, and so taking the time to come to a math talk I'm proud that you folks made it. All right, so here's the motivating question. Suppose that we have a positive definite quadratic form with integer coefficients. Which positive integers are represented by the form Q? That's the main question we'll talk about today. So here's an answer in a classical case. So Legendre proved in 1798 that a positive integer can be written as a sum of 3 squares if and only if it's not a power of 4 times a number which is 7 mod 8. So the first thing to look for is necessary conditions. We say that a positive integer n is locally represented by the form Q if there's a solution to Q of x equals n, where the vector x is in ZP for every prime number p. Another way of saying this is that n is locally represented if there are no modular arithmetic reasons why the form Q cannot take on the value n. So it's a theorem of Tartakovsky that if the number of variables in the form Q is at least 5, then a positive definite form Q represents every sufficiently large locally represented integer n. So that gives a very nice answer saying that the necessary condition is sufficient as long as the number is big enough. I'm interested especially in the case that r is equal to 4. So here's an example in this situation. So let's look at the form Q, which is x squared plus y squared plus 7z squared plus 7w squared. So this form Q locally represents all positive integers, and it also fails to represent 3, 6, 21, and 42. It's not so hard to see that it fails to represent 3 and 6. If the form Q represented 3 or 6, then you would have to have z and w equal 0. But the only way that could happen is if 3 or 6 were a sum of 2 integer squares, which they're not. A simple modular arithmetic calculation will show you that if the value of the form Q is 0 mod 49, that forces x, y, z, and w to be 0 mod 7. It follows from this calculation that Q doesn't represent 3 times any power of 7 or 6 times any power of 7 for any integer k greater than or equal to 0. So this form Q has 4 variables. It locally represents every positive integer, but there are still infinitely many integers that it fails to represent. So we say that a quadratic form Q is anisotropic over QP if when x is in QP and Q of x is 0, it follows that the inputs must all have been 0. So the form on the previous slide is anisotropic at the prime 7. So there's another version of Tartakovsky's theorem that if you have a form Q in 4 variables, first of all, there are only finitely many anisotropic primes. And if you fix a positive integer m, there's a constant which depends on the form Q and the number m with the property that if n is locally represented by Q and the power of p dividing n is less than or equal to m for all anisotropic primes p, and n is larger than this constant, then n must be represented by Q. So every sufficiently large positive integer is represented as long as you put some absolute bound on the power of an anisotropic prime that occurs in the factorization of n. So we're interested now in knowing something about the value of this constant c of q comma m, how it depends on q, how it depends on m. In 1963, Fomenko gave the first bounds for Tartakovsky's theorem that indicated the dependence on q. So to state that, let's introduce some terminology. So I'm going to write my quadratic form Q in the form 1/2 x transpose AX, where the matrix A has integer entries and even diagonal entries. So you can write every single quadratic form with integer coefficients in that form. And I'm going to define the discriminant of Q, d of Q, to be the determinant of the matrix A. I'm going to let n of Q be the so-called level of Q. N of Q is the smallest positive integer, so that n of Q times A inverse has integer entries and even diagonal entries. So Schulze-Pilow proved in 2001 that if n is co-prime to any anisotropic prime, so that's like the case of m equals 0 in Tartakovsky's theorem from an earlier slide, then n is locally represented by Q, then if n is larger than the level of Q to the 14 plus epsilon, then n must be represented. There are a variety of local conditions we can give. We say that n satisfies the strong local solubility condition if for all primes p, there's a vector x in z mod p to the rz, so that q of x is congruent to n mod p to the r, and p does not divide the vector a times x. So I didn't specify here what the r is. We define r to be 3 if p is 2, and r to be 1 otherwise. So Browning and Dietmann, in their 2008 paper from Proceedings of the London Math Society, used the Strukle method to show that if n satisfies the strong local solubility condition and n is larger than the discriminant of Q to the 10 plus epsilon, then n is represented by Q. So I want to mention that Browning and Dietmann's result is a little bit stronger than that. If you assume more about the shape of the form Q, if you put conditions on the successive minima of the lattice associated to Q, you can get stronger bounds. And this discriminant of Q to the 10 plus epsilon is the worst case. I guess I just said that. Okay. All right, so here are the results that I'm going to talk about in this talk. So I have a result back from 2014. If you have an integer which is locally represented by a form Q, and you assume that the discriminant is a fundamental discriminant, then first of all, you can't have any anisotropic primes. And second of all, if n is larger than the discriminant of Q to the 2 plus epsilon, then n is represented by Q. The result that's mentioned above is not effective. In particular, for small enough values of epsilon, I cannot tell you what the implied constant is, and that's because it depends on zero-free regions for GL1 L functions. So my second result is more recent. If you let Q be a quaternary quadratic form, and if you have an integer n that's locally represented by Q, if the GCD of n and the discriminant is 1, which among other things implies n is coprime to all anisotropic primes, then n is represented by Q provided n is at least this big. I have this maximum that depends on the level and the discriminant, and depending on the relative sizes of those, one of these two would be larger. If n satisfies the strong local solubility condition, the condition of Browning and Dietmann that I mentioned earlier, then n is represented provided it's at least this big. We say that n is primitively locally represented by Q if you can find a solution to the congruence Q of x is congruent to n mod p to the k, where p does not divide the vector x. And in this situation where n is primitively locally represented, it must be represented by Q provided it's at least this big. And there's a final case that we can consider. So suppose now that n is locally represented by Q, it's not represented by Q, and it's larger than this quantity. If that's the case, it has to fail to be represented because of some anisotropic prime. In particular, then there's an anisotropic prime p, so that p squared divides n, and n times p to the 2k is not represented for any k. All right. Any questions about these results or about the stuff I've talked about so far? All right. Feel free to stop me at any point if you have a question. Don't feel shy. I want to mention another result that's related to these. This is something that my master's student, Hao-Chen Wu, is working on. Which primitive positive definite quadratic form, quaternary form, represents n the greatest number of times? Intuition might suggest that the representation numbers are larger if the discriminant of the form is small. It turns out that this is not necessarily the case, though. So Hao-Chen has proven that if you fix any finite set of primitive positive definite quaternary forms, then you can find some other quaternary form that's not in your set, R, and some integer n, so that the form R represents n more times than any of the forms Q1 through Qs represent n. All right. So I want to talk, I'm moving into the next section of my talk where I talk about modular forms. I get the impression, given the people running this seminar, that modular forms are something that a lot of people attend this seminar are familiar with, but I do want to not assume too much background. So there's this wonderful quote attributed to Martin Eichler that there are 5 fundamental operations of arithmetic: addition, subtraction, multiplication, division, and modular forms. Here is a picture of a modular form. This is a picture that I made of the J function. So the J function is normally defined on the upper half of the complex plane, but the upper half of the complex plane is conformally equivalent to the unit disk. And the coloration in the picture is based on taking the magnitude of the J function, taking the log of it, and then looking at the first digit after the decimal of the log of the J function. That will tend to infinity, but as the function grows, the colors will move through the rainbow. So what is a modular form? A modular form of weight k, level n, and character chi is a holomorphic function that plays nice with linear fractional transformations. So this is saying f of az plus b over cz plus d is chi of d times cz plus d to the k times f of z for every matrix A, B, C, D, and gamma 0 of n. So I'm going to let capital M sub k be the C vector space of such modular forms, and S sub k be the subspace of Cuss forms. So these are finite dimensional vector spaces. And that's one of the things that makes modular forms so remarkable, is that the spaces of modular forms are smaller than you think they are. So if you have a quaternary form Q and you let R sub Q of n be the number of representations of n by Q, then this generating function, theta sub Q of z, sum n equals 0 to infinity R sub Q of n times Q to the n, where Q is e to the 2 pi I z, is a modular form of weight 2 on gamma 0 of the discriminant of Q with character chi sub discriminant of Q. Actually, we can say more. The level of the form theta sub Q is in fact n of Q, the level of Q. One of our favorite things to do with modular forms is to take an arbitrary modular form and decompose it as a sum of an Eisenstein series in a Cuss form. So coefficients of Eisenstein series, people think of them as being large and predictable. A sub e of n is bounded below by n to the 1 minus epsilon, at least if n is locally represented and co-prime to the discriminant. And it's not so hard to get more explicit formulas for the a sub e of n, although it takes some work, and to get more explicit bounds on the a sub e of n. On the other hand, the coefficients of the Cuss form part are small and mysterious. So the nth coefficient of the Cuss form is bounded by some constant times the number of divisors of n times the square root of n. And sometimes the coefficients a sub c of n are connected with elliptic curves or abelian varieties or Q curves or things like that. So here's an example. Let's take the form x squared plus y squared plus 3z squared plus 3w squared plus xz plus yw. Its theta series is this modular form, which lives in the space of weight 2 modular forms for gamma 0 of 11 with trivial character. The Eisenstein series part of Q can be built using E2 of z and E2 of 11z, It has this formula, 1 plus 12/5 times this sum, which is really just the sum of the divisors of n that are co-prime to 11. And the cusform part of z is 8/5 times this eta quotient, q times 1 minus q to the n squared times 1 minus q to the 11n squared. So the cusform here actually is connected to the 3 elliptic curves of conductor 11. And knowing that, you can get a bound on the A of n, that the A of n is bounded by number of divisors of n times square root of n. And then the cusform part was 8/5 times that. And so from this, we get the bound that r sub q of n is greater than or equal to 12/5 times the sum of divisors of n co-prime to 11 minus 8/5 times the number of divisors of n times the square root of n. So if you're interested in knowing what integers the form q represents, you're interested in knowing when the right-hand side here is positive. And there are only 110 square-free integers for which the right-hand side is negative. If the right-hand side is positive, then r sub q of n must be positive, and that means that n represents q. It's not too hard to check that the form q represents all 110 integers n for which the right-hand side is negative, and from that it follows that q represents every positive integer. So this example is nice. It gives us a clear understanding of the Eisenstein series part, how large the representation numbers are. We'd like something like this in general. So let's talk about the Eisenstein series part first. There's a formula of Siegel that shows that the Eisenstein series part can be written as a product of local densities, beta sub p q comma n. So this beta sub p q comma n, if p is not infinity, is based on the number of solutions of this congruence. Q of x is congruent to n mod p to the k. The local density at infinity is pi squared times n divided by the square root of the discriminant. And we can say more about what this limit evaluates to. If p does not divide the integer n or the discriminant, then beta sub p q comma n is 1 plus big O of 1 over p squared. If p does divide n, but it doesn't divide the discriminant, it's 1 plus big O of 1 over p. And if p does divide the discriminant, it's more complicated. So to get some bounds on this local density beta sub p of n, it's helpful to take your form and diagonalize it. Or at least go as close as you can. If p equals 2, you can't diagonalize an integer quadratic form over z2, but if p is larger than 2, you can. So we'll decompose our form as much as we can into 1 or 2 dimensional pieces of this form. And then I'm going to define this quantity r sub p of q. This is the minimum of the p-adic valuation of the coefficient a sub I plus the entries in the vector x sub I, where q of x is 0. This number is a measure of how anisotropic the form q is. If q is anisotropic at p, then r sub p of q is infinity. But if it's like if r sub p of q is 5, this would be like saying the form is like anisotropic mod p to the 5, but it's not anisotropic mod p to the 6. So now I have a lemma. If q is primitive and n is locally represented by q and the prime is not 2, then if n satisfies the strong local solubility condition, we have this lower bound on beta sub p. If it's primitively locally represented, we have this bound on beta sub p. And in general, beta sub p of n is greater than or equal to 1 minus 1 over p times p to the power minus minimum of r sub p of q and ord sub p of n. We have similar results if p is 2, but we just need to change the constants in the inequalities. So this is a way of translating the assumptions that we're making, the local assumptions about q and n, into bounds on the beta sub p's. So let's talk about the cusform piece now. To bound A sub C of n, we'll use the same approach as was used in older papers of Fomenko and Schulze-Pilow. And the idea is to bound the Peterson norm, which is essentially the L2 inner product of the cusp form C with itself. So Valentin Blomer and George Milichevich show that there is an orthonormal basis for the space of weight 2 cusp forms, with the property that the nth coefficient is bounded by the level of Q to the 1/2 plus epsilon times the number of divisors of n times root n, at least as long as the GCD of n and the discriminant is 1. So our goal is to bound this Peterson norm. If we can bound this Peterson norm, we can parlay that bound into a bound on the Fourier coefficients of the cusp form part. To do so, we're going to use an explicit formula for the Weil representation due to Scheitauer. And this formula will tell you how this modular form theta sub q will transform under any matrix in SL2Z. So to state the formula is kind of nasty. Let's let L be the lattice associated to Q. So we can think of this as the set Z to the 4th, where you have an inner product which is given by values of the quadratic form. This is a way of giving a geometry, a distance to the points in Z to the 4th that comes from the quadratic form. So the dual lattice L prime of L is the set of all vectors in R to the 4th that have an integer inner product with everything in the lattice. The discriminant group is the quotient group L prime mod L. This group is a finite abelian group and it has order D of Q. So we want to choose a number C that divides n of Q. And this will be connected with looking at the Fourier expansion of the form theta sub q at a cusp of the form A over C. I'm going to let D sub C be the kernel of the multiplication by C map from the discriminant group to itself, and D superscript C to be its image. And I'm going to define D superscript C star to be the set of all elements in the discriminant group that satisfy this congruence. I'm going to let W be C divided by the GCD of n over Q in C. This number is the width of the cusp A over C. Okay. So with all the notation on the previous slide, the coefficient of Q to the n over W, so W is the width of the cusp, in the Fourier expansion of theta sub Q hit with this matrix A, B, C, D, is a root of unity times this sum. The sum over all betas in DC star, this root of unity multiplied by the number of vectors in this coset of the lattice where Q takes on the value n over W. So I'm going to let T be the set of all vectors in L prime so that X mod L is contained in DC union DC star. This set DC star, which shows up in this transformation law, is either equal to DC or it's a coset of DC inside the discriminant group. So this T here is really like, you can think of T as being a lattice that contains L. And on that lattice, we can define a quadratic form where we multiply by 4 and then the width of the cusp, and then we take the inner product that is inherited from the inner product on Z to the 4th. So if we do that, this form R, which is connected with this number in the formula, is an integral quadratic form, and we can determine what the discriminant of that quadratic form is. So putting all this together, we get a bound on the Peterson norm of the cusp form of this shape. We have a sum over all the cusps, A over C. We have the number of representations of 4n by this quadratic form R that I wrote down on the previous slide. We have the order of this DC star. And to estimate this sum, we really need to have some handle on how large not just the R sub R of 4n squareds are, but the sum n less than or equal to x of R sub R of n. So to estimate that, I use a trick that was suggested to me by the referee of one of my previous papers. So I thank them, whoever they were, that to bound the sum of r sub r of n squared, the best thing to do is to multiply the sum of the r's by the max of the r's. And then to bound each of these two pieces separately. So the first term is fairly straightforward to analyze. It boils down to counting lattice points inside an ellipsoid, and we get a bound like this. I asked a question on Math Overflow about bounding the max of r sub r of n, and there was a very helpful response that I got that leads to a bound of this shape on the max. So now we've bounded everything we need to. From this, we get a bound on the Peterson norm that looks like this: the sum over cusps A over C, cusp width cubed divided by the magnitude order of this DC star group. And we can bound this, and this is bounded by level of Q to the 1/2 plus epsilon, discriminant Q to the 1/4 plus epsilon, or the level of Q to the 1 plus epsilon, whichever is bigger. And it follows from this that the nth coefficient of the cusp form is bounded by this as long as n is coprime to the discriminant. All right. So putting all of this together, we have that r sub q of n is a sub e of n plus a sub c of n. So the a sub e of n is large and predictable, a sub c of n is small and mysterious. If the GCD of n and the discriminant is 1, then we get this bound on a sub e of n. Under the same condition, the size of the cusp form coefficient is bounded by this. And putting all of this together, we get that r of q is positive if n is at least this large. Okay. So next, I'd like to move on and talk about some applications of this machinery. There's been a lot of interest recently in universality theorems. So let me say what I mean by that. In 1770, Lagrange proved that every positive integer can be written as a sum of 4 squares. This is not so hard to prove if you use the result I mentioned at the beginning about precisely which integers are sums of 3 squares. But Lagrange proved his theorem in 1770, which was 28 years before Legendre proved the 3 squares theorem. So the question is, what other expressions represent all positive integers? So we say that a quadratic form is universal if it represents all positive integers. So we write the form in the Q in the form 1/2 x transpose AX. We say that Q is an integer matrix form if all of the entries in the matrix A are even. Otherwise, we say that Q is integer valued. Yeah, so we say a quadratic form is integer valued if the diagonal entries of A, matrix A, are even. Another way of saying this is that an integer matrix form must have even coefficients for all of the cross terms, but could have even or odd diagonal coefficients. Whereas an integer valued form, there are no restrictions like that. So there's the theorem of Conway, Schneeberger, Bargava that a positive definite integer matrix form Q represents every positive integer if and only if it represents these numbers: 1, 2, 3, 5, 6, 7, 10, 14, and 15. So this was a project that Schneeberger, who was a student at Princeton, worked on with Conway, but their proof was really kind of messy and involved lots of casework, and there wasn't a clean way of solving this problem that they found. And then Bargava came up with his idea for escalator lattices and then published a proof of it in 2000. There's an extension of this, the 290 theorem of Bargava and Henke, that a positive definite integer valued form Q represents every positive integer if and only if it represents these 29 numbers between 1 and 290. So if you have a quadratic form that's positive definite in any number of variables, if it represents the numbers from 1 up to 290, it's universal. It will represent all of the rest. So each of the results I mentioned on the previous slide are sharp. The numbers in the lists in the 15 theorem and the 290 theorem, none of those numbers can be removed and have the theorem still be true. For example, this is a quadratic form in 5 variables, which represents every single positive integer except 290. It's also true that if you have a form that represents every positive integer less than 290, it also represents every integer greater than 290. In addition, Bhargava and Henke determined that there are 6,436 integer-valued quaternary forms that represent all positive integers. So here's a result of mine that addresses a related question. If you assume the generalized Riemann hypothesis, then a positive definite integer-valued form Q represents all positive odd numbers if and only if it represents these numbers between 1 and 451. The reason that it's necessary for me to assume the generalized Riemann hypothesis is that there are 3 ternary quadratic forms that are conjectured to represent all odd numbers, but handling those in an analytic way requires handling the coefficients of weight 3/2 Eisenstein series, which are connected with class numbers. So I have another result that I proved with my master's student, Justin De Benedetto, that a positive definite integer valued form represents every positive integer coprime to 3 if and only if it represents the numbers in this list. And so these are numbers between 1 and 290, but these are not the same numbers between 1 and 290 that were in Bhargava and Henke's theorem. So there are more and different numbers in this list than in Bhargava and Henke's list. So I have another result I'd like to mention in connection with this. So it follows from the proof of the 15 theorem that if you have an integer matrix form, there's a typo in this slide, form Q, which represents all positive integers with one exception, then that one exception must be one of the numbers 1, 2, 3, 5, 6, 7, 10, 14, or 15. You could ask a more general question. What happens if you have an integer matrix form Q that represents every single integer with 2 exceptions? What are those possible exceptions? So here's a theorem proven by 6 different authors: Borowski, Damron, Mejia, Saya, Schock, and Thompson from 2017. If a positive definite integer matrix form Q represents all positive integers with 2 exceptions, then those 2 exceptions have to be one of the pairs on this list. There's a lot of pairs on this list. The one where the second exception is the largest is when m is 10 and n is 250. So this is another result that you can prove using the same sorts of machinery. Let me give you a brief overview into how these things go. So Bhargava's escalator method is used to reduce problems like the ones that I mentioned to a finite calculation involving specific quaternary quadratic forms. So you end up with a list, often a fairly long list. In Bhargava and Henke's case, more than 6,000 quaternary quadratic forms, and you need to explicitly understand the integers that those forms represent. You can use modular symbols to explicitly decompose the cusform part into new forms and to derive an explicit bound on the cusform coefficient. And with that in hand, you can determine the integers represented by a form Q. So here's an example. Let's take this form Q. This form Q, the modular form, has weight 2, level 4,200, and character chi sub 168. The dimension of the space of weight 2 cusforms here is 936. It takes almost a day to take the theta series for Q and explicitly algebraically do the decomposition of the cusform part into eigenforms, and then apply the Deligne bound to each eigenform and get that the nth coefficient of the cusform is bounded by 31.05 times the number of divisors of n times the square root of n. Once you have that bound, it takes 10 seconds to check that Q represents every odd number. So in this case, you have a significant disparity between how long it takes to compute the bound and how long it takes to check that Q represents everything. If there was some way to make it so that this third step took less time and this fourth step took more time, that might be efficient. So there's a method that we can use when the discriminant is a fundamental discriminant, and this is related to one of my own results that I mentioned earlier. Rather than explicitly compute the decomposition of the Cuss form, we do the following. We compute an upper bound on the Peterson norm of the Cuss form C. We do this by looking at the form Q star. This is like the sibling of the form Q. It has the matrix n of Q times A inverse. It will have the theta series for Q star will live in the same space as the theta series for Q. And essentially the theta series for Q star is the theta series for Q hit with the Fricka involution. Then we compute a lower bound on the Peterson norm of G for each new form in that space. So here is an explicit bound on the explicit lower bound on the Peterson norm of a non-CM new form in this space. This comes from the connection between the Peterson norm and special values of the adjoint square L function. The adjoint square L function can be proven to have no C equals zeros. And translating that into an explicit bound, you get this. You might have CM new forms in S2 gamma 0 D of Q. Those are cases where this argument about no C equals zeros breaks down. These are the GL1L functions that made my previous result ineffective. But you can explicitly enumerate those and just check that the same bound is true for those also. There's a horrible formula for the Peterson norm that you get out of all of this machinery as well. So I'm going to define psi of x to be this combination of the K0 and K1 Bessel functions. And then if C of z is the Cuss form part of theta sub q, this is an explicit formula for the Peterson norm of C. And it involves A sub C star of n, the Fourier coefficients of the Cuss form part of the sort of sibling form of Q. So that's eminently computable. We can use this formula and without working too hard, just get a formula for the Peterson norm. So here's an example where I apply this. So here's a quadratic form in 4 variables. The discriminant is 6,780. The space of weight 2 Cuss forms of this level has 4 Galois orbits of new forms of sizes 4, 440, and 1,312. This is the explicit bound we get on the Peterson norm of each new form G. And then we use 101,000 Fourier coefficients of C star. And using that, we can get both upper and lower bounds on the Peterson norm of C. And this will give us a bound which is not optimal, that the nth coefficient of A sub C is at most 1,200 times the number of divisors of n times the square root of n. From this bound, it follows that Q represents every integer larger, every odd number rather, larger than 8 times 10 to the 16. But the computations that we had to do to get this bound only took 3 minutes and 50 seconds, as opposed to like a day with the example I talked about previously. Once we have that, checking up to this bound only requires 22 minutes and 29 seconds. We don't have to actually check every single odd number larger than 8.3 times 10 to the 16. We only have to test maybe 2 billion such numbers. But fortunately, Jonathan Hankey wrote a lot of very fast C code that could do these things efficiently. So to summarize, if Q is a quaternary quadratic form and n is locally represented by Q, if the GCD of n and d of Q is 1 and n is larger than this quantity, then n must be represented by Q. You can obtain stronger bounds if d of Q is a fundamental discriminant. We also have other sorts of bounds with different local conditions on n. And these methods can be used to determine precisely which integers are represented by quaternary quadratic forms of large level. So thank you very much for coming. It was a pleasure to speak.
All right. Well, let's thank Jeremy. We can clap virtually. A couple of us have our microphone on. Any questions for Jeremy?
I would have one.
Go ahead, Michael.
So, first of all, thanks. That was a very interesting talk indeed. So I understand the bottleneck for the computations is basically sometimes this decomposition of your cusp form contributions into eigenforms, right?
Yes.
So this might be a very silly question. There are ways to compute Peterson norms without knowing that decomposition. So for example, Paris does this in its built-in machinery for computing this with a Haberland type formula. Henri Cohen has some very interesting papers about this. And have you tried at all whether that would help in any way?
I've thought about a variety of ways of computing these Peterson norms, and I imagine that these things could help. The modular symbols code in Paris is fairly new, and so I haven't played with it very much.
No, I think it doesn't really use modular symbols at all, if I understand correctly.
That's correct, yes. I think the way that Paris computes with modular forms is it tries to represent things as products of Eisenstein series.
Right. So, okay.
Well, I have a question. I wonder, since you use the adjoint square of things and stuff, there's been a lot of exciting recent work by Jack Thorne and I guess Newton, and Jesse has done stuff on the functoriality of the symmetric power L functions. Is some of that useful in either getting more explicit things or removing some of the assumptions that you might need in some cases to study some of these things?
So the short answer is that yes, it is useful. One thing in particular that's important is that if you want to explicitly compute, so I'll go back to this theorem. If you want to where did it go? If you want to work out an explicit version of this theorem, then you need to know something like, if you have a new form in this space, you need to know precisely what its symmetric fourth power L function is. And the exact form of the functional equation for that. And so these functorial liftings are useful in that regard, because then you can actually use the local Langlands correspondence to compute what exactly the symmetric fourth power L function is for these. But this has been known for some time by work of Henry Kim.
Okay.
So it's not clear to me that that Jack Thorne's more recent proof of the functoriality for all symmetric powers is something that can be used to get more insight.
I see. I didn't realize that. So you only need the fourth power, and that was already known before, essentially? Okay.
That's correct.
All right.
I have maybe two questions. So the first one, I guess, in these universality theorems, for example, you did the odd and the coprime to 3. Is there going into that? Yeah, if you let's say you choose some set of integers, you've chosen odd and coprime to 3 here. Is there some way to predict beforehand what this set of numbers you need to represent is going to look like? For example, is there something coming from these weight 3/2 L functions that if you choose your sets well, you can get down this set of numbers you have to represent to be something small, or is it kind of you just have to do each one case by case?
There's a little bit of randomness in what the large elements in the set end up being. But in terms of knowing how big the set is or what the largest element will be, it depends a lot on the presence of small elements in your set.
Okay.
So understanding something about, say, quadratic forms that represent 1, 2, 3, 4, and 5 would probably be easier than either of these results.
Okay. Got it.
The other thing, though, is so in terms of whether or not the something about your set will determine something about the integers, sorry, the ternary quadratic forms that you need to worry about. So with the coprime to 3 case, we got lucky, and that all of the ternary quadratic forms that arose in that situation turned out to be regular ternary quadratic forms whose representation behavior was already understood.
Okay. Yeah, that's kind of, I mean, that's kind of what I was asking towards, like, is there maybe you work backwards and say, hey, what weight 3 halves things are connected to something nice, and then does that somehow lead back to some like nice set of integers that I'm trying to represent?
Yeah. So there's some things that you can say in that regard. For example, if you pick some integer k and you take your set of integers you're trying to represent to be all multiples of k, there is no ternary quadratic form that represents every single multiple of k.
Okay.
It's like too dense a set of integers for a ternary quadratic form to represent. And because of that, you would have no ternary quadratic forms that you have to handle conditionally to do that.
Okay. And I guess my second question is sort of related, but I guess how generalizable are these like universality results? Because I haven't looked into too many of the details, but the main thing seems to be this splitting between Eisenstein series and cusp forms, and then that you can get good bounds on each of those pieces. So for like, I don't know, for example, you have, I think Siegel modular forms have a similar decomposition. Is there like a theorem that says what n by n matrices can be represented by a quadratic form or something like that?
So you can try to, there are a variety of ways you can generalize this. So one thing I'll mention, there's this theorem which Bhargava stated but never actually wrote down a proof of, that says for the integer case, if you have any infinite set S of positive integers, there's a unique minimal finite subset T with the property that a quadratic form represents everything in S if and only if it represents everything in T. Okay. So there's a framework for theorems of this type to be true. The thing that's hard is given S determining T. And I feel like that's mostly a computational challenge.
Okay, but like the statement that something like that exists, that's believable, that should like generalize to kind of whatever setting you'd like.
That's right. Okay. And people have looked at analogs of this for quadratic forms in more variables. So instead of looking at, say, quadratic forms representing integers, you can look at quadratic forms representing binary quadratic forms or quadratic forms representing ternary quadratic forms. And then the right tool in that situation would be to use Siegel modular forms.
Right. Okay.
And there isn't a lot of technology out there explicitly bounding Fourier coefficients of Siegel modular forms, and then the decomposition of the theta series could become more complicated. Okay. But it's certainly something that I expect people to look at some point.
Okay. Cool.
I know that Katrin Bringman did something about bounding coefficients of Siegel modular forms just a couple of years ago, but I don't know.
Interesting.
Very well.
I know that she had one of her earliest papers, I think, maybe it was like from her PhD thesis, was about coefficients of either Hilbert modular forms or Siegel modular forms.
Yeah. She wrote like some small thing just a couple years ago, so I'm not sure like how much it beats previous things or exactly what the results are, but I think that was just a couple years ago. But I'm not up to date on what's like the current state of the art in the Siegel modular form stuff. Any other questions? Okay. Well, if not, let's thank Jeremy again for a beautiful talk.
Thank you again for the opportunity to speak.
Yeah.